Hey everyone, welcome to class. This is Alaverga Alex here. So today we're going to be talking about how to decompose a vector. As a reminder, yesterday we learned about what vectors are. Remember that a vector is an object that has a length, which is also known as its magnitude, and a direction. Recall we talked about a position vector, and a position vector helps us locate points in 3 space, or 2 space as well. We touched on the difference between a vector and a scalar. Scalars are like numbers. For example, the number 2 or pi. Now, we talked about some notation for vectors. We use the arrow to denote a vector. The hat denotes a unit vector. And unit vectors have length 1. And the magnitude of a vector has notation bars, like so. You also might see it as the double bars. Either one is fine. It depends on which textbook you're using, really. So vectors are described using angled brackets. So for example, the vector in R2, so this vector lives in R2, this is called the component form of the vector v. Okay, but there are other ways in which we can write vectors. Now let's figure out how to do that by decomposing a vector. So the goal is to write a vector in terms of scalar multiples of other vectors. So to do that, we need to introduce something called the standard unit basis vectors. We call these I hat, j hat, k hat. So imagine 3 space, which is comprised of 3 perpendicular axes, the z-axis, the y-axis, and the x-axis. So the I, j, k hat are the unit vectors in the x, y, and z directions, respectively. So we imagine moving 1 unit in the along the positive x-axis. We call this the I hat basis vector. Likewise, we move 1 unit in the positive j-axis direction, and this is called the j hat basis vector. And we move 1 hat in the positive z-axis, and that's denoted as the k hat unit basis vectors. So, as we'll see, we're going to be able to describe any vector as a linear combination of scalar multiples of the I, j, and k hat basis vectors. Alright, but to do that, we also need to make sure we're on the same page about what a scalar multiple of a vector is. So here, C is some constant, some scalar. So this is a number. And what we're really doing is we can think about scalar multiples of vectors as stretching a vector by some factor of the absolute value of this scalar. So if C is negative, that just means flip the direction of the vector v. For example, if this is our vector v, minus v simply means flipping the direction of v. And 2v would mean take 2 copies of v itself. Like this. 1, and that's about 2. So when you hear the word scalar multiple of a vector, just think stretching this vector or flipping and stretching the vector. So let's do an example. Now, what does the scaled vector 3i hat look like in 3 space? Well, first, we know that I hat is the coordinate basis vector that points in the positive, along the positive x-axis. So let's start there. Now this factor of 3 tells us that we want to stretch this I hat basis vector by 3 units. So we have 1, 2, 3, and that's about 3 I hat, right? Okay. So now let's consider another vector Let's say it has components 2, 1, 3. So how would you draw this? Well, first, I will move 2 units along the positive x-axis. So let's say this is the number 2. So first I move 2 units this way. And then I'm going to move 1 unit along positive y. So from x equals 2, I traverse 1 unit along positive y. And then from x equals 2, y equals 1, I'm going to move 3 units up along the z-axis. So let's say this is 3. This vector tells us where to go, in other words, which direction to travel, and how far in that direction we should travel. And this is precisely what I meant by, in the first video, where I said that vectors give us a notion of where to go, right? Okay. So then by scalar multiplication and vector summation, we can write the vector v as 2 units in the I direction, plus 1 unit in the j direction, plus 3 units in the k direction. So we can write v like this, or we can write it in component form. V equals 2, 1, 3. Okay, so hopefully that's clear. Let's do a practice problem now. Now earlier I told you all what a unit vector notation looks like. We call that u hat. And I mentioned that we define a unit vector to be a vector of length 1. So the notation we use is the bars. But how exactly do we calculate length, and what even is it? So let's create some space here. Okay, a little bit more. So the length of a vector in R3 at least, or Rn more generally, is given by an extension of the Pythagorean theorem. So for v equals abc, the length of v is the square root of the sum of its squares, a squared plus b squared plus c squared. And that is what we mean by the length of v. And this is a positive number because you can't take the square root of a sum of positive numbers and somehow get a negative number. Okay, so going back to the question, what if we want to find a new vector u that is of length 1, but it's in the same direction as v from earlier? How do we do that? Well, all we need to do is get rid of its length, right? It has too much length. We need to scale it by 1 over the length of v itself. So let's try this with the vector 1, 2 in R2. So in order to obtain a vector that has unit length that points in the same direction as v, we just take v hat and define this to be the vector v itself, the direction. But we want to pretty much cancel out the length of v, which is the magnitude. So calculating this, we have 1, 2 over the square root of 1 squared plus 2 squared. This is just 1, 2 over the square root of 1 plus 4, which is 5. And that gives us a unit vector. So be my guest to make sure that you see that this vector actually does have length 1. Okay. What if somebody gives you a vector and says, I don't really want length 1, I want length 27 or 36 or whatever, but in the opposite direction of v? What do we do then? Pause. Think. So from earlier, we calculated a new vector, v hat. Let's see, that was 1, 2 over root 5. And this vector has length 1. and it points in the same direction as v, which was the vector 1, 2. But we are interested in finding a vector of length 27. So what we do is we say, okay, v hat has length 1, so if I want a vector of length 27, just multiply that by 27. Just stretch it by a factor of 27. So we stretch v hat by a factor of 27. That takes care of the vector of length 27, but we also have to make sure that it's in the opposite direction of v, so we apply a negative sign to switch the direction. So what would that look like? So our new vector, let's call it w, would be 27 times v hat, and that minus sign to make sure that we are switching the directions. Okay, so quick note, when we add, subtract, or scale vectors, we have to do it component-wise. So that just means perform this operation component by component. So let's do an example. Let's say we have the vector 1, 2, 3, and we want to add it with the vector 4, 5, 6. Well, all we do is we add components. So the x components first, 1 plus 4 is 5. Then we do the y components, 2 and 5, 7. And then we just have the z components, 3 and 6, which is 9. Hence component-wise. Okay. So in the next video, we're going to talk about how to tell if two vectors are parallel or perpendicular. So if you like this video, give it a thumbs up and comment and subscribe. Thank you. See you next time.